So what we're going to look at today is oxidation numbers. So just a quick reminder of what we just talked about. Oxidation involves the transfer of electrons. And there's two ways to show this. One can be using a half equation. So for example, if I was to burn magnesium, the magnesium is turning from its element into ions, which we know is 2+. And this, while the element is balanced, does not balance the charge, so I can put 2 electrons here to make a half equation. This is one way to show that magnesium is being oxidized because electrons are in the product side of the reaction, so they're being lost, they're being given away. And in that case, magnesium burning in the presence of oxygen, or air, the oxygen is therefore picking up those electrons. And we can show that by having our oxygen turning into its ion oxide. You notice I've got 2 of them there because there's 2 here. This has got a -4 charge, so this side does too. Because the electrons are on the reactant side, they're being gained. So the oxygen atoms in the oxygen molecule are gaining 4 electrons to become the oxide ions. Well, that's one way to justify, and another way is to assign what we call oxidation numbers. And these are actually even easier once you know how to assign them. These are even easier for seeing if oxidation or reduction has occurred. Because if an oxidation number increases, if it goes up, then you've got oxidation. And here's one that's really easy. If it goes down or reduces, you've got reduction. All right? Now, I'm going to quickly go through how we can assign it to something like these ones here, because these are actually quite easy. Any element has an oxidation number of 0. Okay? So that's my first little rule, as it were. Elements their oxidation number, which I'm going to call ON, is equal to 0. So, up here, in both cases, magnesium is 0 and oxygen is 0 because they're both elements. Okay. Then, the next thing that makes this a really good, easy example is that this has actually got an oxidation number of +2 and this has got an oxidation number of -2. Now, if I have a look at what's written there, that looks pretty similar to something that's written next to the magnesium and the oxygen. And that is that the charge of the ions seems to be the oxidation number. But these are very special cases because they're what we call monatomic ions. They're made up of one atom, one type of atom. Okay? So monatomic ions the oxidation number equals the charge. Okay, but you notice that it's +2, not 2+. You notice that it's -2, not 2-. Okay? Oxidation number and charge, while they're related, are not the same thing. Now it gets a bit trickier when we get to things that are made up of more than one atom. So I'm going to take something that is made up of some oxygens, because it's a nice easy one to start with. I'm going to start with carbon dioxide to work out the oxidation number of each atom in this. Now, oxygen is quite an easy one, because oxygen, because of its place on the periodic table, it's either 0 or it's -2. There's one exception to that rule, and only one exception, and I'll tell you that in a moment. So, oxygen can either be 0 or -2. Is oxygen an element in that? No, it's not, because it's bound to something. Elements can only be bound to their own kind. So therefore, it's got to be its other option. So here, oxygen is -2. So oxygen's going to be -2. I'll write them in there. Okay, so each of those oxygens is -2. Now, if I was to tell you that carbon, in that case, must be +4, let's see if we can work that out, how that works out. Right, what we have here is a molecule, all right, which means it's got no charge at all. If I go back to this rule here about ions having oxidation numbers that equal charge, that means that if I add up all of the oxidation numbers in there, it must equal charge. It's a molecule, so the charge is 0. So I'm going to have carbon plus 2 oxygens equals 0. I know that oxygen, this is just algebra now, sadly. I know that oxygen is -2, so carbon plus 2 times -2 equals 0. And now it's just maths. 2 times -2 is -4. So something minus 4 equals 0. That's why it's 4. So the sum of the oxidation numbers in a molecule must add up to 0. So here's another rule. Alright? So that's not too bad. So therefore in carbon monoxide, CO, what would the oxidation number of carbon be in that case? +2. Fantastic. Okay, going to get rid of CO2 and have a look at something else. What about something like ammonia, NH3? It has no oxygens, so I don't have that rule to use. It doesn't have ions in it. It's not made up of ions. So I can't use the monatomic ion idea. Okay? So I need another rule. Starting to get a few rules here. But, again, this is quite nice. Hydrogen is +1 apart from when it's bound to metals, and then it's -1. Well, nitrogen's not a metal. So therefore, each of those is +1. So what do we think, using this rule, the nitrogen would equal? -3. Fantastic. So I end up with -3 for my nitrogen using the same rule. So 3 minus 1 minus 1 minus 1 equals, -3 plus 1 plus 1 plus 1 equals 0. So that works out. So therefore, I have to have a little rule. Hydrogen, again in compounds, the oxidation number is +1. Okay. Time for the one exception. The one exception to that. So these two rules here have a bit of a hierarchy. Okay? So hydrogen is +1 when it's in compounds, and oxygen is -2 in compounds. But then we get this thing here, H2O2, hydrogen peroxide. Now, those of you who are mathematical geniuses in the room have worked out straight away that those two rules can't exist together in H2O2. So this is where this rule has got a wee exception. In this molecule, and only this molecule, oxygen is not going to be -2, it's going to be -1. This rule comes before this rule. This rule is more important, in other words. So, in this one case, hydrogen is +1 and oxygen is now -1. Alright? Got one more thing to cover. That's our last sort of rule, as it were, but I'm not going to write it up as a rule. What if I had something like an ion with more than one atom? Okay, so polyatomic ion. Let's take sulfate. Now, using the molecule rule, we can actually work this one out quite easily. What do the oxygens have to equal? -2. How many of them are there? 4. Okay. So sulfur is what we don't know. We know that's -2. So we can actually write that in. Well done. So sulfur plus 4 times -2. What do you reckon it has to equal? Fantastic. It has to equal -2, the charge. Okay? So, something, the oxidation number of sulfur, -8 has to equal -2. So sulfur equals +6. Okay? And that is our answer.
Sorry, just a quick thing. Oxidation, that's and reduction. So oxidation is the lost electrons. So you're writing it up there as positive.
No, I'm saying if the oxidation number increases, you know it's oxidation. It's another way for you to prove it. This is why we learn oxidation numbers. If oxidation number goes up in a half equation, you know that something or other is being oxidized. Okay? Alright, so, and if it doesn't change, then you know that it's not oxidation reduction.
Why does it have to equal? Why does the sulfur one have to equal -2?
Good question. Okay. In a molecule which has got no charge at all, it has to equal 0. So if you've got something made up of more than one atom, but it does have a charge, so it's an ion, then rather than equaling 0, it equals the charge of the ion. Okay? Very good question, thank you. Alright, so the last little rule, as it were, is that the sum of the oxidation numbers in an ion must equal the charge of the ion. And the nice thing is you will meet ones with oxygen or with hydrogen in them. Alright? So that's oxidation numbers in a nutshell. So the next thing to do is to actually practice doing them and to look at some of the half equations from the things we've done earlier to see if you can assign oxidation numbers to see which things are being oxidized and which things are being reduced.